Hello, and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 6th, 2025. We're looking at an ICLR conference paper published about 3.5 months ago, titled LoRA-RITE, Robust Invariant Transformation Equilibration for LoRA Optimization. This paper tackles a key issue in LoRA, or low-rank adaptation. Current optimizers aren't transformation invariant, meaning different factorizations of the same update can lead to inefficient learning. LoRA-RITE aims to fix this. Okay, so the authors illustrate this problem in Figure 1. It shows how the Frobenius norms of the LoRA factors A and B, these are the two smaller matrices LoRA uses, behave during training with common optimizers. You can see factor A's norm stays pretty flat, while factor B's norm changes significantly. This highlights that imbalance in learning, which is exactly what transformation invariance, the core idea here, aims to address. Alright, so moving to the empirical evidence. Table 1 here lays out the experimental results on the supernatural instruction dataset. We can see for both Gemma 2B and Gemma 7B models, LoRA-RITE, their proposed optimizer, consistently achieves the highest scores across various tasks, and notably in the global metric. This really backs up their claim that achieving transformation invariance leads to significantly better performance compared to standard optimizers like Atom. And this advantage isn't limited to just the supernatural instructions dataset. This table here expands the view, comparing LoRA-RITE with optimizers like Atom and Lamb across more common sense reasoning and math benchmarks, like HelloSwag, ArcChallenge, and GSM-8K, which is grade school math. Across both Gemma 2B and 7B models, LoRA-RITE consistently posts the highest scores, underscoring its broad effectiveness. Now, a crucial question with any new optimizer is its computational cost. Table 4 here shows the number of training steps per second for different optimizers. We see LoRA-RITE's speed, for instance 0.878 steps per second for Gemma 2B, is quite competitive, especially when compared to Atom's 0.948. This demonstrates the performance gains don't come with a prohibitive increase in training time, keeping it efficient like common first-order methods. So we've seen it's efficient, but how does it perform under different conditions? Table 3 here presents an ablation study, which tests the method by varying LoRA ranks, that's the R in their complexity, and different model architectures. For both Gemma 2B and the larger Mount 5 XXL, with ranks 4 or 16, LoRA-RITE consistently outperforms Atom and Lamb. This really underscores its broad effectiveness and robustness. Alright, so to rigorously evaluate LoRA-RITE, which uses a novel preconditioning on, quote, unmagnified gradients, essentially gradients made invariant to how the LoRA factors are scaled, helping achieve transformation invariance. The authors employed several standard benchmarks. Table 6 here lays these out, listing datasets like HelloSwag and GSM-8K, their sizes, and evaluation splits. This provides context for those strong results. So, wrapping up our look at LoRA-RITE. It's clear this method effectively tackles that critical transformation invariance problem for LoRA, which, as a reminder, is low-rank adaptation for fine-tuning. By ensuring consistent updates regardless of internal factor scaling, LoRA-RITE delivers significant performance boosts seen across benchmarks like GSM-8K without a heavy computational price. That's all for this AI Research Roundup. Thanks for tuning in.